Hello everyone, my name is Nan Cheng from School of Telecommunications Engineering, Xidan University. Today I'll talk about our latest work on federated learning. The title of this presentation is RingSFL, an adaptive split federated learning towards taming client heterogeneity. If you have any question, you can ask anytime. My talk will be divided into the following three parts. In part 1, the background includes the introduction of traditional machine learning methods, federated learning, and split learning, as well as some current problems and challenges. The second part is about our research details, where I will introduce our proposed RingSFL scheme, including training process, model split scheme, and some discussions. The third part is the experimental process and the results. I'll start with background. As we all know, artificial intelligence is currently being used more and more widely in our lives. Artificial intelligence technologies such as deep learning have been widely used to train data models to realize smart IoT applications such as smart healthcare, smart transportation, and smart cities. The traditional centralized machine learning approach is shown in this figure. Users need to upload their own data to the cloud for the centralized training, and the trained model is sent to the users. This paradigm is currently widely adopted, where a central server holds all the data and trains a model with abundant computing resources. However, there are also many limitations. For example, in many applications, training data is generated by users, and uploading this raw data to cloud servers may compromise user privacy. Now, more and more people are beginning to pay attention to privacy. From our own considerations, we don't want to upload our own raw data. In addition, the transmission of raw data causes a large amount of communication resources to be consumed. This approach not only results in an unacceptable computing burden for some clients, but also wastes some computing power. So in order to solve the above problems, Google proposed a federated learning paradigm in 2017. You can see the training process from this figure. First, the server initiates the process by initializing a global model and sending it to the participating clients. Second, each client trains the model using its own local dataset and uploads the updated model parameters to the server. Then, the server aggregates the received model parameters to generate a new global model, which is then sent back to the clients. Finally, this process is repeated until the global model converges. So in this process, we don't pass the original data, only the model parameters. This can effectively protect the privacy of the user's original data and improve communication efficiency. However, there are also some challenges in the federated learning research. The heterogeneity of federated learning is widely studied, including client heterogeneity and data heterogeneity. Most clients in federated learning systems have varying computation power and battery power. At present, some studies have proposed effective methods to alleviate the heterogeneity of clients. Besides client heterogeneity, data heterogeneity is another important issue. It refers to not identically and independently distributed data distribution among different clients. As shown in the figure, there are three different data distributions, such as the smartphone, CAV, and the metaverse users. In addition, privacy leakage is also a major problem in federated learning. In 2019, MIT proposed that some information is hidden in the gradient, and the private training data can be reconstructed from the shared gradient used in the federated learning. we can see that as the number of iterations increase, the original data is restored to 500 iterations. In the year 2021, NVIDIA proposed a grand inversion method to achieve image batch recovery from gradients. We can see from the figure that the image is very similar to the original image. So we should consider the impact of privacy leakage of the system. Split learning was proposed in 2018. The split learning mechanism divides the model into two parts, one for the client and one for the server. Then the client feeds the local data into the model and initiate the forward propagation. Next, the client sends the output of the split layer and the corresponding labels to the server. The server then inputs the client's output into the local model and continues the forward propagation to generate the model output. Finally, the server utilizes the model output and the labels to calculate the loss value and initiate the back propagation. There are some advantages and disadvantages of split learning. The model located on server side can achieve higher accuracy due to its ability to learn from multiple clients. And split learning is more suitable for deployment on edge devices than federated learning because the models located on the client side are typically smaller. But split learning often encounters convergence issues on non-IID datasets, and the training latency is affected by the number of clients. This will make parallel training difficult. Based on the above background, there are some methods proposed which integrate federated learning and with split learning. These methods leverage their respective strengths and create a new architecture for distributed learning that is suitable for edge network environments. Hence, we propose a new federated learning scheme called RingSFL. The proposed structure of the RingSFL system is illustrated in the figure. The system comprises a central server responsible for model aggregation and N clients that perform cooperative training. Every client has its own training dataset. The clients are organized in a ring topology wherein adjacent clients can directly communicate with each other using technologies like device-to-device communications. In addition, the clients can communicate with the server to download and upload the models as in the original federated learning paradigm. Note that it is straightforward that the construction of the ring topology plays a critical role in determining the system performance. However, this paper mainly focuses on investigating the fundamental properties of RingSFL, and as such, a ring topology is arbitrarily set with the investigation of its construction left as future work. The training process of RingSFL consists of three parts: the initialization, local training, and the parameter aggregation. This slide shows the initialization. Initialization is conducted at the beginning, and before the training begins, the server needs to configure the entire system. The participating clients need to upload their own status information to the server, including the size of the data sets, D sub I, and the computation power, C sub I. Then the server determines the configuration parameters of each client based on the status information. There are two required configuration parameters: the propagation length, and the aggregation weight. Among them, the calculation method of the aggregation weight is the same as Fed averaging used in the conventional federated learning. and the aggregation weight of each client is proportional to the size of the datasets, and the clients with larger datasets have larger weights. The propagation length is a unique parameter of the proposed RingSFL, which is used to specify the number of layers that need to be propagated in the local model each time the forward propagation is performed. For example, if the propagation length of a client is 3, it means that the client only needs to propagate 3 layers in the local model. We set the propagation length to be proportional to the computation power of each client, where W represents the number of layers in the model. If a client's computing power is weaker, its propagation length is correspondingly shorter, thereby reducing its computation load and avoiding delays in other clients' training efficiency. The specific derivation of the propagation length will be introduced in the following parts. After the initialization is completed, the server sends the determined configuration parameters and global model to the participating clients. After the client receives the configuration parameters, it starts the local training process. We illustrate the forward and backward propagation process during the local training with the figures. This figure shows the RingSFL system with 3 clients to collaboratively train the multi-layer perception with 6 fully connected layers. The propagation lengths of the 3 clients are set to 2, 1, and 3 respectively. First, we divide the forward propagation into 3 phases, namely the starting phase, the relay phase, and the stop phase. Let's take the client 0 as an example. The forward propagation process is shown with the blue arrows in this figure. In the starting phase, client 0 samples a mini batch of the data from the local datasets and feeds it into the local model for forward propagation. And the number of layers of propagation is specified by the propagation length. For example, the propagation length of client 0 is 2, so it propagates 2 layers in the local model. Then in the relay phase, client 0 transmits the feature map output from the second fully connected layer of its local model to client 1. Then, since the propagation length of client 1 is 1, it forward propagates one layer on the local model of client 1 and transmits the resulting feature map to client 2. Similarly, client 2 forward propagates 3 layers on its local model to obtain the final model output and transmits it back to client 0. Finally, in the stop phase, client 0 uses the received model output and the corresponding level to compute the loss value. This is a complete forward propagation process for client 0, while the forward propagation process for other clients are similar to that of client 0. The back propagation process is similar and can also be divided into 3 phases with the same names. Let's also take client 0 as an example. Its back propagation process is indicated by the dark blue arrow in the figure, dark blue. The starting phase is mainly used to start the back propagation process. Client 0 sends the loss value calculated by the forward propagation and its own aggregation weight to client 2, and starts back propagation. This is followed by the relay process. Since the propagation length of client 2 is 3, it starts back propagating 3 layers from the upper layer in the local model based on the loss values, gets the gradients corresponding to the 3 layers and the weights, then weights them with the aggregation weights of client 0. Subsequently, client 2 sends the gradients of the display layers to client 1, Similarly, client 1 backpropagates 1 layer and client 0 backpropagates 2 layers to complete the backpropagation process. It can be noticed that during this propagation process, the computed gradients are distributed over these 3 layers, thus achieving better privacy performance. The gradients are weighted because since the gradients obtained from backpropagation of client 0 are distributed over 3 layers, all the 3 clients, it becomes infeasible to weight the updated parameters directly as in the Federated averaging mechanism. And so we use weighting the gradient during the training process. Finally, in the stop phase, the 3 clients update the corresponding parameters based on the gradients obtained by backpropagation. The backpropagation processes for client 1 and client 2 are the same, and the forward and backward propagation processes are carried out simultaneously for the 3 clients. In each communication round, each client performs multiple forward and backward propagation to update the model parameters. After the local training is completed, the clients upload the locally updated model parameters to the server for aggregation. Since we have weighted the gradients during the training process, the server only needs to average the model parameters during aggregation. When the aggregation is finished, the current communication run is over, and the server will start the next communication run and repeat all the steps. RingSFL contains multiple communication runs during training until the global model converges. Now we'll talk about the derivation of the propagation length. This propagation length we denote by M the amount of the computation required for one iteration of the model locally. Since there are a total of n clients, the computation required for all models in the system to iterate once is M times n. Since we aim to mitigate the straggler effect by allocating the overall computation, we assume that the ratio of the computation allocated to the ith client to the total computation is P sub I. Then the amount of computation for the ith client is P sub I times M times N. And the amount of computation for that client is then the time required for this client to complete the computation task is the amount of the computation divided by C sub I. C sub I is the computation capability of the client I. To minimize the computation time consumed by the straggler, we can formulate the optimization problem on the left. This is a min-max problem which we can transform into a linear programming problem and obtain the solution as here. We can see that the optimal computation load for client should be proportional to its own computational power. So we set the propagation length of each client as the product of the optimal computation load ratio and the number of model layers. In our experiments, we also found that there is a phenomenon of overlapping layers in the training process of RingSFL. That is due to the different propagation lengths of different clients. There may be some neural layers that are trained by data from multiple clients at the same time. For example, as in this figure, client 0 and client 1 collaborative to train the MLP containing 6 fully connected layers. The blue arrow in the figure indicates the forward propagation path of client 0, and the red arrow indicates the forward propagation path of client 1. It can be noticed that in the local model of client 1, its third and fourth fully connected layers are passed by both the blue and the red arrows, which are trained by the data from both client 0 and client 1, and we refer to these two layers as the overlapping layers. During backpropagation, the gradients of client 0 and client 1 on these two overlapping layers will be aggregated together. The gradients of these two layers have a high aggregation frequency, which also means that the gradients of these two layers are more reliable. Therefore, we set the learning rate of the model by layer, so that the overlapping layers have a larger learning rate, which allows them to have a larger step size on the reliable gradients, thus driving the model to the global optimum. The final experimental results also show that such a sighting can effectively improve the performance of the global model. As discussed previously, conventional FL still faces the risk of privacy leakage. In the RingSFL, on the other hand, clients upload the blended models, where different layers in this model are trained by feature maps from different clients. So eavesdropping on models uploaded by a single client cannot obtain the complete model parameters of this client. The only possibility of privacy leakage is that there is a super eavesdropper who can eavesdrop on all the models uploaded by all the clients, and then reassemble all the local models to restore the complete parameters. We assume that the probability of the link between the client and the server being eavesdropped is denoted by E. The probability that all uploaded models are eavesdropped is the cumulative product of E. Then we can derive the curve of the privacy leakage probability with the number of clients on this figure. It can be seen that the privacy leakage probability decays exponentially with the number of clients, and the RingSFL ensures a relatively high security performance, even with a very high eavesdropping probability, such as E equals to 0.4. Okay, next we present the experimental results of RingSFL. In order to comprehensively evaluate the performance, we further implemented the prototype system based on the simulation system. The simulation system is mainly implemented in Python, and the model is constructed and trained using PyTorch. The prototype system contains two main types of clients: the weak computational client, participated by Raspberry Pi, and the strong computation client participated by the desktop PC. These nodes work together to form an ad hoc network and make a ring communication topology by modifying the routing table. The communication between the nodes mainly works in the 5 GHz band, and the spectrum width used for communication is 40 MHz, resulting in a D2D communication rate of 135 megabits per second. Since the computational power of the server that aggregates the parameters has little impact on our system, we use a laptop to act as this role. We then use the commonly used MNIST dataset and the CIFAR-10 dataset for the evaluation. The models used for evaluation include ResNet 18, VGG 16, LeNet 5, and the AlexNet. These two figures show the convergence performance of the proposed RingSFL on IID and non-IID datasets using the ResNet 18 model. We compare the RingSFL with benchmark algorithms, including SplitFed, the vanilla FL, and the vanilla SL. The RingSFL V2 means the RingSFL with the adaptive learning rates for the overlapping layers. The left figure presents the performance of RingSFL on the CFR10 IID dataset utilizing the ResNet 18 model. After an equal number of communication rounds, the RingSF V2 achieved the highest model accuracy compared to the benchmark algorithms. This validates the outstanding convergence performance and the effectiveness of the proposed scheme on the IID dataset. RingSFL V1 also performed well, slightly lower than the V2, but still outperformed Vanilla FL and Split FL, highlighting its superior convergence capability. The utilization of overlapping layers in RingSF V2 allows for gradient aggregation, optimizing parameters towards the global optimum and resulting in improved model accuracy. The right figure illustrates the impact of diverse data distributions on the convergence performance of the proposed scheme during training on the CFR10 non-IID dataset, using also the ResNet 18 model. RingSFL V2 consistently maintained the highest model accuracy compared to benchmark algorithms. The RingSFL V1 further emphasizes the significance performs similar to the Vanilla FL, while Vanilla SL and Simplified struggle to converge on the non-IID datasets. This underscores RingSFL's adaptivity to the non-IID data distributions. Overall, the results demonstrate that the RingSFL exhibits the most optimal convergence performance compared to the benchmark algorithms. The performance disparity between the V2 and the V1 further emphasizes the significance of overlapping layers in the RingSFL. In subsequent slides, we will provide a more clear and detailed explanation of this aspect. On this slide, we show the training results of RingSFL on different models, and it is evident that RingSFL consistently maintains the highest model accuracy compared to the benchmark algorithms. This conclusion holds true across various model architectures, further demonstrating the robustness and effectiveness of the proposed model. To evaluate the impact of overlapping layers on model accuracy, we conducted a series of experiments in the RingSFL V2 with different propagation length configurations. By unevenly distributing the propagation length, we gradually increased the number of overlapping layers. Specifically, we set different propagation lengths as the legend shows. We can observe the effect on model accuracy in the above experiments. As shown in the two figures on this slide, the impact of overlapping layers on model accuracy is clear. When the propagation lengths are more unevenly allocated, resulting in more overlapping layers, the model accuracy improves as this one. This phenomena can be attributed to the higher reliability of gradients in the overlapping layers. Importantly, this conclusion holds true for both IID and non-IID datasets. The observed phenomena can be explained by the training process of RingSFL, where overlapping layers accumulate gradients from different clients. This accumulation enhances the reliability of gradients in the overlapping layers, leading to more effective optimization of parameters towards the global optimum. On this slide, we present the top 1% accuracy of different propagation lengths for various models. The table further validates the conclusion we obtained on the previous slide regarding overlapping layers. This slide shows the impact of different DFT communication rates on convergence performance and time cost, using the ResNet model as an example. In the left figure, the convergence performance of RingSFL in RingSFL at different D2D communication rates is illustrated. It is evident that as the D2D communication rate decreases, the time required for RingSFL to reach the same accuracy increases accordingly. However, it can be observed that as long as the D2D communication rate is sufficiently good, the proposed RingSFL achieves convergence in a shorter time compared to the vanilla FL. Specifically, RingSFL takes less time to convergence than the vanilla FL when the D2D communication rate is greater than or equal to 10 Mbps. This finding is further elucidated in the red figure, which demonstrates the time consumption of RingSFL to complete a training run at different communication rates. To validate the adaptability of RingSFL to system heterogeneity, we conducted additional experiments on prototype system to evaluate its reduction in convergence time and improvements in the energy efficiency. The left figure depicts the reduction in convergence time, where RingSFL achieved an impressive 61.6% decrease in training time compared to vanilla FL. This is due to that by properly allocating propagation length, RingSFL can balance the computational load across the system and efficiently mitigate the straggler effect. It is important to note that split fed and vanilla SL exhibited shorter training times than RingSFL, thanks to their model split mechanisms. These mechanisms offload a significant portion of training tasks to servers with high computational power. In our experiments, the client computational load of split-fed was 1/5 of RingSFL in each round, and the client computational load of vanilla SF was 1/20 of RingSFL. However, it is crucial to emphasize that despite their shorter training times, split-fed and vanilla SL could not achieve comparable performance in terms of model accuracy and user privacy. The red figure, titled Energy Consumption in Different Devices in the Communication Round, clearly illustrates RingSFL capability to control the power consumption of the FL system. It is evident that RingSFL as compared to vanilla FL increases the energy consumption of PC nodes, while reducing the energy consumption of Raspberry Pi nodes. This energy distribution is a result of RingSFL's ability to balance the computational loads among clients. This observation highlights its effectiveness in conserving energy for battery-powered devices, thereby extending the lifespan of the whole system. To demonstrate the superiority of RingSFL in privacy preserving, we conducted an experiment to evaluate its ability to resist the data reconstruction attacks. The LeNet neural network was employed, and the CFR10 dataset was utilized. The system comprises 5 clients with a propagation length configuration of L0 to L4 with 33222. The results of the data reconstruction attack is shown in this figure, with the first row corresponding to the attack on vanilla FL, and the second row corresponding to the attack on the RingSFL. It is evident that after 80 iterations, the training data in the vanilla FL can be successfully reconstructed, whereas the attack on RingSFL fails to recover the training data. This outcome is primarily attributed to the adoption of a blended model transmission in RingSFL. which involves fragmented and mixed model parameters, making it challenging for attackers to extract information about the training data. As a result, RingSFL effectively prevents the recovery of the original training data, thereby preserving the user privacy. Finally, I will provide a list of important relevant references. For those who are interested in this work, you can refer to these references for more detailed information. Okay, that's all for my talk. Thank you for listening.